This video will be a follow along to do some practice problems on continuity. I'm assuming that, or I'm making this video with the assumption that my viewers are reviewing for the AP exam, not going to go from scratch, basically. So we got to remember this formula first of all. I'll just state this. The definition of continuity is f is continuous at x is equal to a if limit as x approaches a, f of x is equal to f of a. We got to remember this. This is the definition. Okay, so this is a follow along, as I said. So I would recommend you try the problem first. Once it appears on screen, pause the video and try it, and then unpause it to see how I work through it and to check your answer as well. All right, so here's number one. All right, so we're given these three functions. We need to analyze why it's discontinuous, and at those points of discontinuity, is it removable or non-removable? Okay, so number one, how do we know that something's discontinuous here? Well, probably at the switching point. Okay, so this is where we're going to use the definition of continuity. So we need, okay, so I wrote not equals, but pretend there's an equal sign. We need limit as x approaches 3, g of x to be equal to g of 3 if it's continuous there. Okay, so how do we find this limit? We can find the one-sided limits to see if this two-sided limit exists. Okay, so if we take the limit from the left, as x approaches 3 from the left is this top branch over here, from the left is values less than 3. Okay, so we plug in 3 as our x. 2 times 3 minus 3 is equal to 3. Okay, 6 minus 3, which is 3. And from the right, that's this bottom branch, we plug in x is 3, we get the limit is 2. The limits don't match. That means the two-sided limit does not exist. Okay, that's what I said right here. So how in the world will the definition of continuity be true? How can something that does not exist equal g of 3? G of 3 is defined. It is 2. Okay. So does not exist is not equal to 2, clearly. So it's not continuous there. Now, what type of discontinuity is this? Is it removable? Is it not? This is not removable. It's actually, you might have learned this, it's a jump discontinuity. I don't really think the types of discontinuity are important to know, but since this problem asked it, I'll go over it. It's not removable, it's a jump. So if you actually graph it, you'll see that it jumps from 3 to 2, essentially. That's why we found those limits. Or that's how we interpret these limits, I should say. Okay. You can convince yourself by graphing it, and you'll see it's a jump discontinuity. So a jump discontinuity is not removable. The only removable type of discontinuity is if it's a hole. Okay. For part B, is a rational function, so we probably want to factor. We factor to the bottom, we get 3x plus 1 times x minus 2. So if you remember from pre-calc or algebra 2 or something like that, if something cancels, there's a hole. Okay, but there's actually two discontinuities before that. There's one at x is 2, and there's one at x is negative 1/3. Okay, so the one at negative 1/3 is a hole, as I was saying. Okay, a hole is a removable discontinuity, and I'll go over a little bit in the next slide, a bit more detail. So if you're curious about that. Okay, the other one, remember this is just a vertical asymptote. So asymptote is not removable. You can think of it like that. Okay. Sometimes people call this an infinite discontinuity. Again, I don't think the names are important as well. I don't think the names are important, not as well. But anyway, okay, so let's go over, if you're curious, a little bit more on why it's a removable discontinuity. So hopefully you understand what a hole is, or I guess I'll explain it a little bit again here. Okay, so if we take the limit as x approaches negative 1/3 of our b of x, our function b of x, okay, like in the other problems when we were calculating limits, since it's 0 over 0, we have to do something. So one technique is to factor and see if anything cancels. So these would cancel, and we're left with x over x minus 2, and then now we plug in, we would get 1 over 7, okay? So there is actually a hole at this exact point, negative 1/3, comma, 1, 7, okay? If you remember how holes are, it's like or this function, if you really want to simplify, it's x over x minus 2. But for domain purposes, x cannot be negative 1/3 still, because this is part of the original, okay? So this b of x looks really close to x over x minus 2, except there is a hole at x is negative 1/3, and that hole is exactly this point. So you can think of it as this one point got removed from the function x over x minus 2. That's why it's called removable discontinuity. You can just add this point back, and it'll be continuous at that point again, at that value of x again, I should say. Okay, 1C, how do we do this? There's actually two ways to think about it. If we try to find the limit first, how would we do that? Well, the top we can factor, and we can rewrite square root of x minus 5 squared as absolute value of x minus 5, because it's plus or minus x minus 5. So we can just write it as absolute value of x minus 5. Okay? Because remember, absolute value could be either the inside could be positive or negative. We don't know. Okay? So it's the same representation. Okay, so if we find the one-sided limits, so if we approach 5 from the left, it would be negative 1. If we approach 5 from the right, it would be 1. So the limit does not exist, and similar to that, I think it was 1a, how can something that does not exist equal to some value? Okay? Well, actually, let's word it a little differently, because h of 5, notice, also does not exist. It's undefined at x is equal to 5. It's undefined. So that's why I'm backtracking. Does not exist equal does not exist. So it doesn't quite work like that. But there's no value for h of 5. Our domain restricts us from going there. The domain of this function. We can't divide by 0. Doesn't matter that the top is 0, so we can't divide by 0. The 0 over 0 thing was for limits. We're approaching. So that's a little different. This is actually 0 over 0. We can't divide by 0. Even I don't know how to divide by 0. Okay? So since the definition of continuity is not met, it's not continuous at x equal to 5. It's actually, I believe, a jump discontinuity, so it's not removable. Okay? Because, again, we looked at the one-sided limits. Okay. Number 2. I don't think this is too important, but this was a practice problem in this test prep book. So here is what it was. It asked to draw some function that satisfies these conditions. Okay, so go ahead and try it first on your own. Here's just the sample one, or here's a sample one. This is just from the test prep book itself. Okay, or even before we analyze this graph. Okay, so let's go back here. We're also asked to describe the continuity. So from just what they provided here, we can tell that there's a discontinuity at x is equal to 0 because there's a vertical asymptote there. As x approaches 0 from the right, it approaches negative infinity. From the left, it approaches positive infinity. So it's going to be an asymptote there. Okay? And also notice that limit as x approaches 2, f of x is 1. However, f of 2 is equal to 4. So that definition of continuity is not met because these two need to be equal for it to be continuous. So those were the clues right away for what's not continuous. Okay? So now we graph it. This is one possible case. So you can see limit as x approaches 2. Should be minus 1. Did I make a typo? If this is the case, minus 1. Yeah, minus 1. Actually, yeah, let me put it before I forget. Actually, the give f minus 1 is here. Did I make a typo in this as well? Okay, let's start looking. Actually, no, okay, yeah, this should just be minus 1, my bad. Sorry for the confusion. Okay, maybe, yeah, you can go try this again. But okay, this should work. Yeah. As x approaches 2, it's negative 1, yeah? From 2 from the left and 2 from the right, it's negative 1, okay? f of 2 is 4. That's up here. We shade that in, but we leave this open. Okay? F is increasing though, so it's going to look something like that. And then we know that as x approaches 0 from the right is negative infinity, 0 from the left is positive infinity. We were saying there's the asymptote there. Okay? And what else do we know? F of negative 1 is 0. F of 3 is 0. Okay? So this is a sample function. And it's increasing in its entire domain. Okay? Sorry for the typo. Okay? Yeah, if this was positive 1, then it would have to decrease to 0. So that wouldn't work. So my bad. Okay. Again, I don't think this is too important though. So if you got stuck, I wouldn't worry about this too much, to be honest. Of course, it would be great if you know how to do this though. Okay, this I would argue that is much more important. I've seen many problems on this before. Find the value of k that makes p continuous if p of x is this piecewise function. So go ahead and do this one first on your own. All right. How did I approach this? Well, we need to use the definition of continuity. It's possibly discontinuous at the switching point x is equal to 4, so we need limit as x approaches to 4 of p of x is equal to p of 4. We need that to be true. Okay, so what's the left-hand side? What's this limit? Let's evaluate the one-sided limits. So from the left, we are on this top branch. So we plug in x is 4. We get minus 2 plus k. From the right, we're on this bottom branch. We would get 5 when we plug in x is equal to 4. So for the limit to exist, a two-sided limit to exist, these two need to match. So we just set them equal to each other. Minus 2 plus k is equal to 5, so k is equal to 7. Okay, and then with k is 7, the p of 4 would be 7 as well, because it's continuous from the left. Okay. Again, this is a very standard problem. I've seen this many times, even whether on the AP exam or just calculus class at some other school, like a community college or even university level. This is a very typical problem. All right. Hopefully this was helpful and this was good practice for you. Please give this video a like if it has helped you in any way, and hopefully see you in another video as well. Bye.